In this video, we're going to look at vectors in 3 dimensions. By convention, when we're in 3 space or R3 just means that we have 3 dimensions and our numbers are coming from the real numbers instead of complex. We use what we call the right-hand rule, in which the positive x-axis comes toward us, out of the plane. The positive y-axis is to the right, and the positive z-axis is straight up. And it comes from, if you put your right hand around and rotate around, cupping your fingers and rotating around, that your thumb will always be in the positive x, and the rotation from x into the y is going to be positive as well, from positive x to positive y. So that's what it means to be the right-hand rule. So now we're going to be in ordered triplets. So instead of having x and y, we have x, y, and z. So we'll have a location in the x direction, a location in the y, and a location in the z. We are now going to formally define what each plane is. A plane that is the xy plane is anything that has x's and y's and z is 0, where x and y are any real numbers. An xz plane is similar. In this case, the y is 0 and the x and z are any real numbers. And of course, the yz being the last, where the x is 0 and the y and z can be any real numbers. So this is an example of one of the planes. Now these planes are on the x-axis or the y-axis or the z-axis. I can have a plane that is not necessarily on each axis. I can move it off to some other place, and it can be described with an equation of a line, or it could be described with vectors, and we'll see that later. So in R2, we had quadrants. In R3, we have octants. So now this first space is octant 1, in which I have all of the x, y, and z are all positive. And then you can see as I go along, I have to have every combination of x being positive and negative, y being positive and negative, and z being positive and negative. The distance between 2 points is going to change slightly. In this case, instead of just having the differences in the x's squared, the differences in the y squared, and the differences in the z squared, or x's and y's only, now we have to introduce the z's as well. The midpoint also changes. It's going to be the summation of the 2 x's divided by 2, the 2 y's divided by 2, the 2 z's, and divided by 2. So I'm asked to find the distance and the midpoints between these 2 points. We're going to do the easy one first, which of course is the midpoint. So let's start with the midpoint. The midpoint is just going to be the 1 plus 10 divided by 2, because I'm taking my x values and I add them together and I divide by 2. I'm going to now do my y values. So I have negative 1 minus 3 divided by 2. And then lastly, my z's, which is 4 plus 9 divided by 2. So my midpoint between these is going to be 11 over 2, or if you want, you can do 5.5. And then negative 4 over 2, which is negative 2. And then 13 over 2, and if you prefer, again, you can do 6.5. The distance formula, it doesn't matter whether you take your x2s minus the x1s or the x1s minus the x2s. It doesn't really matter, provided, of course, you're consistent. So I'm going to do 1 minus 10, the quantity squared, plus negative 1 minus a negative 3, the quantity squared, and then plus my last one, which is 4 minus 9, the quantity squared. So this is going to be equal to the square root of, I'm going to do 11 squared, which is 121, plus, and then it's going to be negative 1 plus 3, which is 2, so 2 squared is 4. And then 4 minus 9 is negative 5 squared, so plus 25. And this will then be equal to 121 plus 4 plus 25, which gets me the square root of 150. Now within this 150, I know that I can divide by 25. And so this is the same thing as the square root of 25 multiplied by the square root of 6, which is 5 root 6. And so there is the distance formula in the in 3 space. Now, if we consider this rectangular box with one of the vertices is at the origin, so that's saying this right here, the origin now is x, y, and z. If the point opposite the vertex is 2, 3, and 5, so that's this point right here, we want to find the coordinates of the other pieces of the box. Well, we know that this first value is the x, the second value is the y, and the third value is the z. That means this must have gone in the x direction too, and since I'm on the x-axis, zeros for the other 2 points. Similarly, this point right here must be on the y-axis, so it'd be 0, 3, and 0. This point, since it's on the xy plane, must be the point 2, 3, and 0. This point, because it's on the YZ plane, must be 0, 3, and 5. This point, which must be on the XZ plane, must be 2, 0, and 5. And this one, because I am on the Z-axis, must be 0, 0, and 5. So there's all the vertices. To find the length of the diagonal of the box from O to A, so I'm going to go from O to A, that's what they're asking me for, is this. From O to A, this distance is going to be equal to, because my origin all has zeros, I don't have to worry about doing the 0 minus 0, or excuse me, the 0 minus 2 squared, the 0 minus 3 squared, the 5 minus 0 minus 5 squared. It's simply going to be 2 squared plus 3 squared plus 5 squared, which is going to give me the square root of 4 plus 9 plus 25, which gives me 38. There isn't much I can do about 38. It's 2 times 19, which are both prime, so I'm going to leave it like that. So a few things to note that when there are 3, 2 lines can be parallel because they're on parallel planes. But that doesn't mean like we normally would say that parallel in 2 space. If I take these 2 lines that are running on parallel planes and I look down on them from looking down, straight down the x-axis or z-axis, so that'd be like right there's a z-axis, looks like they're actually crossing each other. But they're not in R3. They are when they're projected down onto R2, but they are not in R3. So the plane is a space that is parallel to the xy axis and will contain the points A, B, and C, where Z is equal to C is the plane. The plane in the space is parallel to the xz axis will contain this point A, B, C again, of course, and can be represented by y is equal to b. So this is the plane I'm talking about. The plane that is parallel to the xy axis will be the equation z is equal to some number. So this is what I mean by that. Let's come back up here. So this region right here on is the xy plane. If I were to draw a plane where I've got z is equal to 3, here is z is equal to 3. Not drawn well. And you can see that this plane here is running parallel to the xy plane. So that's what they're saying here, is that if I want to find a plane that's parallel to the xy plane, it'd be z is equal to a number. If I want a plane that's running parallel to the xz plane, then it's going to be y is equal to the number. And if I want a plane that is running parallel to the yz plane, then it's going to be x is equal to the number. The way you can remember this is what you want to run parallel to, if we're talking about an xz or the yxy or the yz, it's going to be the value, the variable that is not part of the plane you want it to be parallel to. So if you run it parallel to the yz, then it's x. The xz, then it's y. The xy, then it has to be the z. Also, when we're thinking about circles, in 3 space, 2 circles can be interconnected. In this case, you can see on the left, where I've got this circle here and I have this circle here. When I project these circles onto the xy plane, here is my red circle, that's this one here, but my blue circle ends up just becoming a line segment here. So in 3 space, things are not necessarily touching, but when they're projected on one of the other planes, it does look like they are. So let me do this. It keeps rotating and it drives me nuts when it does that. Okay. So let's take a look at what an equation looks like at x equals 0. When x equals 0 in R1, we have a line graph, and x equals 0 is just a dot on the line graph. This is an R1. In R2, when x is equal to 0, we have the line y, x is equal to 0, so it's a line which ends up becoming the x, or the y-axis. In R3, it ends up becoming the plane. It is the yz plane when x is equal to 0. And we know the equation x is equal to 0 describes all the points that satisfy this, which is x is 0 and y and z can take on any real number. We can do the same thing when we have y is equal to 0 and z is equal to 0. So the plane in a space that is parallel to the xz plane, again, is like I did before, is z is equal to c, y is equal to b, and x is equal to a. If we want to find the equation of the plane that goes through the points 1, -2, -5, 3, 8, -5, -2, 7, and -5, the first thing we're going to do at this point, because we haven't learned norming yet, is look to see if there's any number that they all share. And then in this case, they all share that -5. This equation then would be z is equal to -5, because all of them share that -5. My next example is they want to find a plane that is uniquely determined. So first of all, a plane is uniquely determined by 3 distinct non-collinear points on the plane. Collinear means that they can't be on the same line. So they have to be non-collinear, which means they can't be on the same line. And so we want to find 3 distinct points that describe the plane z is equal to 3. So what I do is, without having any linear algebra behind me, is I think of the easiest points. The easiest points that I know will be linearly independent, and again, not knowing if you hadn't have had linear algebra, that's okay, is the easiest one is the ones that would have been, when we're talking about vectors, would have been the unit vectors, making sure that the z part is 3. So if we think about unit vectors, it would have been 1 for the x, 0 for the y, and 0 for the z. But in this case, we want it to be 3 because we need it to go through the plane z is equal to 3. Similarly, I have 0, 1, and 3, and then my last one is 0, 0, and 3. Now, I know that all 3 of those points are not on the same line, but they are on the same plane. Now, a line is uniquely determined by 2 distinct points on the line. Consider the intersection of the planes x is equal to -2 and z is equal to 3. Find 2 distinct points on the line. So I'm going to do something similar like I did before, is I need to make sure that my 2 points has the x as the -2 and the z as the 3. So the first distinct point I could have is -2 and 0 and 3. Another one that I could have could be -2, 1, and 3, or I could have had -2, 3, and 3. But what I want to include is this one here, where I have this 0 for the y part, and I have to ensure that both my x and my z are the same values of -2 and 3. Now, when 3 planes come together, it can join as a plane, it could be a line, or it could be a point. Or it could be an empty set. There could be 3 planes that are running parallel to each other and there's no points of intersection. We want to find the intersection points of the planes x is equal to -1, y is equal to 3, and z is equal to 9. Well, the only point in which these are going to intersect is when x is -1, y is 3, and z is 9. Okay, so that's kind of introduction to planes. We're now going to be asked which point of these 3 points is the closest to the xz plane. The one that is the closest to the xz plane is the one that has the smallest absolute value of the y value. So to answer this, it's the one with the smallest absolute value of y. So I look to see which one has the smallest absolute value of y, and it happens to be this one. The absolute value of -8 is 8. And the absolute value of 13 is 13. The absolute value of 15 is 15. So my answer is A, point A. Similarly, which point is the furthest from the YZ plane? So I want the largest absolute value of x. And so I look for the largest absolute value of x, and that happens to be C, because the absolute value of -2 is 2, the absolute value of 4 is 4, the absolute value of -9 is 9, so the answer is C. And then I ask myself, which point is on the YZ plane? For the point to be on the YZ plane, the XY plane, the Z must be 0. And none of them have a Z of 0, so the answer is none. Let's talk about vectors now. So just like when we had vectors in R2, we're going to have vectors in R3. We have the components of the vectors where we use those almost like inequality brackets, x, y, and z, where we assume if it's in that form that we are in standard position, which means our tail starts at the origin, and our tip is the point, lands at the point 2, 4, and 1, or x, y, and z. The unit vectors in each direction are going to be 1, 0, 0, 0, 1, 0, and 0, 0, 1. We kind of talked about that earlier. And so as we did before, we use linear transformation like we did in R2. So my vector x, y, and z. Multiplying, we have the x. So first we start out with the way that we do the addition. So x plus the zeros, the y with the zeros, and the z with the zeros is taken into consideration that we can do scalar multiplication. So it must have been x times 1, y times the 1, and the z times the 1, which gives me xi plus yj plus zk. We want to find the vector component of the unit vector form, which means I want the ijk stuff, with an initial point of P and a terminal point of Q. So you have to pay attention who you start with, because like before, when we did this in R2, we take our tip, which is Q, and subtract off the tail, which was P. So my P to Q will be equal to -4 minus 2 gives me -6. 3 minus a -2 gives me a +5. And 2 minus 6 gives me a -4. In the ij form is -6i plus 5j minus 4k. Now, I want two non-parallel vectors that are parallel to the z-plane. This goes back to my unit vectors. My unit vectors, the ones that will run parallel to the z-plane, are the ones that the z equaling 3 plane are the easiest ones to do, are my unit vectors, which would have been the one in the x direction, 1, 0, and 0, and the one in the y direction, which is 0, 1, and 0. Find a vector perpendicular to the plane z is equal to 3. The one that's perpendicular is the one that must cross it perpendicularly, so this would be an easy unit vector, which would have been 0, 0, 3, or 1, or 7, or whatever. They're all going to run perpendicular, because if you draw the plane here's the plane in the z direction, not done well, obviously, and then any vector that is going to be perpendicular like that, which would be anything that runs only in the z direction. Find one vector parallel to the line of intersection of the planes x is equal to -2 and z is equal to 3. The easiest and simplest one that's going to run parallel to these intersecting planes is going to be the one that's not mentioned, which is the y. So we could use 0, 1, and 0. That would be the easiest one that is not going to be mentioned. See, I've got a plane that's going in the x direction, and I have a plane that's going in the z direction. The one that it's going to run parallel is the one that is the y, because it's the one that's not mentioned. When we're talking about vectors in 3 space, it's still the same kind of algebra that we did before. We get the scalar multiplication, we get the vector addition and the vector subtraction. Our magnitude, assuming that we are in standard position, is just going to be the square root of each individual piece squared. And the unit vector, of course, is my magnitude, which is what that was, divided by each one of my pieces, provided, of course, I'm not talking about the 0 vector. We still get the 0 vector in here too. It's just now the 0 vector will be in 3 space. So let's start out with a nice simple multiplication of a scalar and a subtraction. So if I'm asked to find v, which is -2, 3, and 4, minus 3 times my w, which is 1, -1, and 0. I have -2, 3, and 4 minus, I'm going to go ahead and multiply the 3's through, so it's 3, -3, and 0. And now I'm just going to do a subtraction of the components. So -2 minus 3 more is -5. -3 minus a -3 gives me a +6, and 4 minus 0 is 4. So that's my final answer. Now, we can now do applications. And we have to do the components like we did before. So when we do the components on this, we have to pay attention. Oh, I need to find the unit vector. Oh, the unit vector of v. Sorry, I moved on. I forgot I needed to do the unit vector of v. The unit vector of v is going to be the magnitude of v, which is going to be the square root of -2 squared plus 3 squared plus 4 squared, which is going to give me the square root of 4 plus 9 plus 16, which gives me the square root of 29. So my unit vector u in the v direction is going to be 1 over the square root of 29 multiplied into my v vector, which was the -2, the 3, and the 4. So this is going to be equal to -2 over the square root of 29, comma, 3 over the square root of 29, and 4 over the square root of 29. So there is my unit vector in for the v vector. Okay. Now, express the force as a vector in vector component form. So in this case, my y or my z is 0. Since my z is 0, here's the direction of z, here's the positive x, and here's the positive y. My vector is on the xy plane only. So since the vector is on the xy plane only, I go +3 in the x and +4 in the y. So here's my vector. So going from the origin to P being the point, so it's actually truly in the correct form. What I know is, because I'm only really working in x and y, I'm just going to rewrite this in 2 space. I go in this direction 3. I go in this direction 4. So in other words, my resulting vector is the vector 3, 4 in 2 space. And that's because my z is 0. So here is my y and here is my x. Now I can break this apart in terms of its magnitude, sine, and cosine of the angle. But I'm not actually going to find the angle. I'm going to get the ratio of what the angle would be. I'm going to call this theta. I know the cosine of theta must be equal to 3 divided by, then I have to figure out the length of this vector, or in other words, my r. Since I have a 3, 4, and we know the missing piece is 5, so we know that this is 5, right? Because it's a 3, 4, 5 triangle. We know the sine of theta is going to be the 4 over 5. Now what they're telling me is I have this force. That force is a magnitude. So I have this 50 as my magnitude multiplied by the cosine of my angle, the sine of my angle. Now I can go through the point of finding the sine and cosine, but I don't want to because I have the ratio. I have a replacement for cosine theta. Cosine theta can be replaced with this 3 over 5. Just like the sine of theta can be replaced with a 4 over 5. So this is equal to 50 multiplied by the 3 over 5, and then comma, the 50 multiplied by the 4 over 5, which gives me 30 and 40. But I'm technically in 3 space. I was able to work in 2 space to get my answer, but I'm technically in 3 space. So my true answer for the first part in component form is the 30, the 40, and the 0. Now to find the angle between them, I didn't have to do it to answer the first part, but it is asking me for the angle between them. And I can use either this one or this one and do this cosine or sine inverse or tangent if I want to. I could get the tangent, which is the 4 divided by the 3. It doesn't really matter. I'm going to use the top one. And so I have the theta is equal to the cosine inverse of 3 over 5. And so to answer my second part, my theta, and what do they want it in degrees? Okay, so I got to make sure my calculator is in degrees first of all. So look on the mode of your calculator. And of course I'm not, I'm in radians. So let me go ahead and change that. And I'm going to do the cosine inverse of 3 divided by 5. And I get theta to be, and they want it to the nearest integer, so I get theta to be 53 degrees. All right, so those are my answers for that. Now, I have this 5 kilogram pendant chandelier, and it's designed in such that the alabaster bowl, which is this thing down here, is held by 4 chains of equal length, and the assumption is that it's also an equal distance around the curvature or the outside rim of the bowl. We want to find the magnitude of the force of gravity acting on each chandelier, and then we want to find the magnitude of the forces of the tension for each of the 4 chains. Assume the chains are essentially vertical. So that's going to help us a little bit when we go to solve this. So first we have this force acting down. And then we have all the tensions. We have this tension 1 and this tension 2, this tension 3, and my last one being tension 4. Okay? So to answer the first part, we know that the force, we're going to call this the force coming down. This force, because it's moving away from the origin, I'm moving away from the, it's moving away from the shape, it's coming down toward Earth, is truly a negative. So the force is equal to the negative of the absolute value of my force multiplied by k. That's how we write it as a vector. It's going straight down. And the absolute value of, or the magnitude of the force is going to be the weight, which is the mass multiplied by gravity. So my force is the mass multiplied by gravity. I know kilograms is a mass quantity. It is not a force or weight quantity. So this is going to be equal to 5 multiplied by 9.81 to make sure we're in the same units. And so I get 49, and then the units for my weight or the force is in newtons because we're in the metric system. So I've answered the first part. The first part is the magnitude of the force, and it's 49 newtons, and it is negative because it's heading toward the Earth. Now, the next part is the one that's a little bit more interesting, is that we know that each one of these tensions that we have are going to be equal. So all the tensions are equal. So I know that tension 1 comma tension 2, tension 3, and tension 4 are equal because we're assuming that these are all the same length and they're equal distance around the outside of the bowl. So we have to assume, we can make the assumption that they're all the same length. And so since the chandelier is not falling down, we know that this is a static system. That means there's no movement. That means the summation of all the forces has to equal 0. So the force of gravity and our mass, our force in the downward direction, plus all of the tensions going in the upward direction. Now remember, all of these tensions are the same length, equal distance all the way around. And so all of those tensions are the same, and there's 4 of them. So I'm just going to write this 4 of T1, and this has to equal 0 because we're in a static system. We are not moving in any way, shape, or form. Now let's take a look at one of the tensions. We're just going to work with T1. Because we're all the same, we're just going to use T1. Now, if I look at the bowl, here's the bowl. I'm just the rim of the bowl. And it's connected somewhere up here in the chandelier space. And this is directly down, straight down. This is the tension here. This is T1. And it's in this direction because it's going away from the, it's going in the opposite direction of my gravity. I can break this up into 2 components, this component and this component. I'm going to call this A, I'm going to call this B, because I can break it up into the 2 components just like we did when we're in 2 space. So I know that my tension T1 is going to be the A component plus the B component. Now I'm going to subscript these because even though all of our tensions are the same, we do need to talk about what happens as we go around our rim. We also have this other tension. We're going to call this T3. Now this T3 also has a B component. It also has an A component. This is my B1 and my A1. This is my B3 and my A3. If I take a look at the way I've drawn this, these are my y-axis. Then these are my x-axis, and I wrote z. It should be my x-axis. My x-axis. And of course, this is my z-axis. What I know is that my B1 minus my B3, because it's going in opposite direction, is going to be 0. And that is the summation of the forces in the y direction, because they're going to counter each other out. Similarly, this T3 and T4 are going to have something similar with their B's. So the B of T2 and the B of T4, they're going to cancel themselves out, and this is a summation of the forces in the x direction. Now this is not going to be the same when we are doing it in the z direction. I have all of these A's, right? I have A1, A2, A3, A4, A5, and etc. The summation of the forces in the z direction still has to equal 0, so that's not a surprise, but I have 4 of the A1, A2, A3, A4, and A5. They're all the same. They all have the same value, so I'm just going to write it as 4A. And then plus the force, not the sum, the force in the y direction from, or z direction from above, which is my weight. Now remember, my weight is hanging down. So this is going to be equal to 4a sub 1 minus my 49 newtons. Now A1, the way I've drew it, can be wrote in terms of the sine and cosine of the angle formed. So let's call this angle right here alpha. So if that's the angle alpha here, then this is the angle alpha here, which means that it's not going to be sine, it's going to actually be cosine. So I'm going to replace a sub 1 is going to be equal to the tension in that direction times the cosine of my angle, which is alpha. So I have 4. My a gets replaced with T1 cosine of alpha minus 49 is equal to 0. So then 4 T1 cosine alpha is equal to 49. So then T1 is going to be the 49 divided by 4 the cosine of alpha. And that is going to be the tension on each of the chains. And that's what we were doing. Again, the reason I did this replacement is because I don't want the A component. I want to know what the tension is. The A component is going to be the magnitude, which is the tension, multiplied by the cosine of alpha. And that's only because I put alpha there. If I would have said this is the angle alpha, which I could have done that, then I would have had sine here. So it just depends on how you defined your angle. Just want to say that. All right, so let's talk about spherical on the, why can't I get rid of this? Just to give me a moment. There we go. Move that up. Really? Move that out of the way. There we go. No, go away. Okay. Whew, okay. Now we're going to look at spherical, which is the set of all points an equal distance from a fixed center, where all the points now are x, y, and z. So we're not a circle anymore, we're a sphere. The sphere in 3 space is x minus a squared, y minus b squared, z minus c squared is equal to r squared, where a, b, c is the center. If we're asked to find the equation of the sphere in standard form, who has a diameter of -1, 5, 7, -5, 2, and 9, the first thing I'm going to need to do is I'm going to need to find my center, and that's the midpoint. So if these are the endpoints of the diameter, then the center is going to be located at the midpoint. So I take -1 minus 5 divided by 2, 5 plus 2 divided by 2, and then 7 plus 9 divided by 2. So my center is going to be located at the -3, 3.5, and 8. Now I want to find the radius, so I can find the diameter and divide it by 2. I could find the distance from the center out, but then I'm going to be working with decimals, and I'm not a fan. So what I'm going to do is I'm going to find the distance of the diameter. So the distance formula, and I'm going to be looking at the diameter. So I'm going to have -1 minus a -5, the quantity squared, the plus 5 minus 2, the quantity squared, plus the 7 minus 9, the quantity squared. 7 minus 9. 7 minus 9, the quantity squared. Now this is the diameter. So I then have to divide by 2. So this is going to be equal to, well, I've got 4, the square root of 4 plus, that gives me 9, and that gives me, let me see, 2, so the first one is 16. First one is 16. It's 4 squared, which is 16. And then my last one is 4. So this gives me the square root of 29. Now, that's the diameter. My radius is going to be half of that, so it's going to be the square root of 29 over 2. They ask me to write it in standard form, so I go back to my center. So it's going to be x plus 3, the quantity squared, plus y minus 3.5, the quantity squared, plus z minus, 8, the quantity squared, is equal to my radius squared, so 29 over 4, and that is my final answer. Okay, so there's my final answer for that right there. I'm just going to move this up and out of the way. Find the equations of the planes that just touch the sphere from the previous example and are parallel to the x, y plane, the yz plane, and the xz plane. So we're going to start with the xy plane. XY plane. I'm only going to do this first one because they're all going to be the same. So if I'm looking for the xy plane, and then I'm going to pay attention to this center for the z part, and I'm also going to pay attention to the radius, which is this. So I know it's the z part. For the xy plane, it's going to be z is equal to my center, which is 8, plus and minus the square root of 29 over 2. That will give me a plane that's touching it on the top and a plane that's touching it on the bottom of the sphere. That is going to be parallel to the YZ plane. I would do the same thing for the the XY plane. I do the same thing for the YZ plane. I would take the variable that's missing, which is x. Its centerpiece is -3, and I'm going to add and subtract to it the radius. That way it'd be just touching at the top and the bottom of the sphere in the x direction. So the square root of 29 divided by 2, and I'll let you do the last one, which is the xz plane. So to finish this off, we're going to talk about graphing other equations in R3, and we're going to really spend some more time on this later in this quarter. So we're just going to talk a little bit about these shapes so you can start to visualize what's going on. And I would recommend Geo Algebra .org, I think it is, geoalgebra.org, because it gets you to do it in 3 space, which is really kind of cool. This is from Geo Algebra in 3 space. Now, if I'm given y minus 5 and z minus 6 is equal to 0, then what I really have then is I really have y is equal to 5 plane, and that's this one. Y is equal to 5 plane, because I set each piece equal to 0. Even though they're different variables, that's okay. And then, of course, this must then be the z is equal to 6 plane. Now, when I look at x squared, x minus 2 squared plus z minus 5 squared is equal to 4. On the xz plane, it's a circle, but in 3 space, it forms a cylinder. Because z and y can take on any value, it's an infinite number of values, and because y can take on an infinite number of values, it ends up becoming a cylinder. Lastly, I have this quadratic, which is z minus 5 squared is equal to 4y. On the zy plane, it makes a parabolic shape, but when you introduce the x part, it makes it more like almost like a trough, an infinite trough, if you will, because z gets to take on any value, any real value, anywhere along the x-axis. So that's it for 2.2, and we'll start 2.3 on the next day.